Welcome back to the channel. Today I'm going to introduce another machine learning topic, and this one is neural networks. And so for this, I'm actually reviewing a portion of a book that I'm working on, which is about machine learning algorithms and practice with R. And so on the left side of the screen, you can see there's a few menu items in there. Most of those are not written yet, but I went ahead and put in some content here for the neural networks part. And so I wanted to go over that as soon as it was ready. And I'll be trying to fill in the rest of that, and I'll be revisiting this as I continue to create more content. So stay tuned. And don't forget to subscribe to the channel if you'd like to stay in touch about that. Now, I'm just going to walk through this and describe what I've written so far and talk a little bit about the code that you can see here. And again, the publishing environment I'm using is Quarto. I'm using that to write this book, and I think it's a really good technology for instruction as well, so I'm using it here to teach. And then the language is R. So first thing I want to do is just mention that neural networks are a type of machine learning algorithm, and they can be used for prediction and classification and a lot of different things. And what I wanted to do with this is to just explain how to make one very simply using prepackaged libraries just to get started. And in this particular case, what I'm going to be doing is a classification problem where some data are labeled and separated into two different classes. And then I'll be explaining some libraries that I'm using, what those are for, and then I'll walk through the code on how to build a neural network. So if you haven't built one before, but you have R and maybe an IDE like RStudio installed, you can do this. So let's go ahead and get into it. The first part is that I want to tell you a little bit about the data. It's important to know what the data are about. So this particular data set is about yeast cellular localization site prediction, which sounds like a mouthful. But essentially, this data set has a number of individuals with a number of numeric characteristics and then an associated label of positive or negative. And the negative term is what most of the individuals are labeled as. And so it's not really super important to understand the biology of this, but it doesn't hurt. So I'll look at that in just a moment. As far as the libraries that I'm using, the first one is NeuralNet, and that's for constructing the neural network. The Tidyverse collection of libraries has a lot of different use, and I'm using it mainly for its data manipulation tools like dplyr, stuff like that. There's a library called CA Tools, which provides an easy way to split our data set, and it needs to be split for the purposes of creating a neural network. Imbalance is the library which contains the data set, and in particular, it's named imbalance because the data sets in there are not balanced. They have a large number of individuals of one type or another. So in this case, like I said, the negative type label is much more prevalent than the positive. And then the caret library is a library that has a function in there that can be used to create what's called a confusion matrix really easily. And they're not hard to make, but this one gives a bit more information when it does that. So it's nice. So it's just a little step saver. So the first thing to do, I load the libraries up. I already have them installed on my system. So I just run this set of code to load them up. And then this paragraph describes that I'm bringing in the yeast4 data set from that imbalance library. And it's described as an imbalanced binary data set, which means it's either positive or negative, and the individuals are not evenly labeled. And it contains protein traits for predicting the cellular localization sites. Okay, multiple columns and one binary factor class, which is the two types, positive or negative. And those are used as the predicted variable in this exercise. You can also get this data set from the UC Irvine Machine Learning Repository, which is a great place to check out if you haven't seen it before. And one special thing here, there's a feature, one of these characteristic columns, ERL, which is a binary attribute. And I just removed it to keep things simple. So everything else is numeric. So we have several numeric columns and then one binary class column. And below there's a description of the features. I'm not going to go over that, but just again, remember that ERL column was removed. The features that are already in the data set as is are between 0 and 1. They're all decimal values, so that's good. If they weren't, I would say normalize the data at this point. So after you bring it in, make sure that the values are normalized and they all kind of appear on the same range. So because that already happened, I didn't really worry about that. So here, there's some code to load that yeast data 4 set, yeast 4 data set, and I made sure that it came in as a tibble, which is a nice formatted data frame. And then I removed that ERL column. And then if we just use this head command, we can take a look at it. So this is what we see. Again, as mentioned, there's a class column. You can see that it's a factor, and the first few values here are negative. And then all of these other features are doubles. So these are all numeric values, and that's good. So the next thing I want to do is just take a look at the distribution of the classes. So are they even? Well, I know they're not already, but how bad is it? So using the table function, I can just quickly take a look at that particular column, and we see that there are 1,433 negative individuals and 51 positive. So many, many more negative than positive. So the next thing I want to do here is to split the data set into training data and test data. And because the amount of negative labels in this data set is very high relative to the positive, they won't really appear in this split very prominently on that smaller split in the test data. So I can already tell that there might be some issues with being able to detect positive labels very well, because there just aren't that many that will appear in the training data or in the test data. So stay tuned on that. We'll see how it works. But the way that this happens is I first do this set seed command, and that's used when you have a process that involves some randomization and variability, and this allows you to reproduce that process. So it doesn't matter what number you put in here, so I just put 1. And then I use this sample split command to generate a vector of labels, and the split ratio here is 70-30. It could be some other value, but generally you want much more information in your training data than your test data. So 70-30 sounds good. And the way this works is I can just give it the vector of labels here and then the ratio that I want. So it's conceptually pretty easy to do. And then I can use that information to actually conduct the split. And so here I have two variables, train and test, which represent the training and test data. And the subset command will actually chop up the original data set and then using the membership here. So sample is true, and those values will go into training. And if otherwise, they'll go into the test. So at that point, I have split the data into train and test. And we can check it out with this dimensions function, and we can see that there are a little over 1,000 values in the training data, and a little over about 450 almost in the test data. So we can see there's a lot more in the training data, which is what we want. And the 8 there just refers to the number of columns. So the next thing to do is to train the network model. So It's not super exciting in terms of code because it's already packaged up into a library, so there's not really a whole lot to look at here. But the important thing is that we will be focused on this class variable. Again, we're looking for negative and positive labels here. So we are doing essentially, it looks like a regression in terms of the way the code is written. So we have class and then this little tilde, and then the dot just means everything else in the data set. You could write out the variables like variable 1 plus variable 2 plus variable 3 if you wanted to. But in this case, I'm just going to do this on everything else. So we have class, and then the data is set to be our training data. And then this next part, hidden, is referring to hidden layers in our network. So visually, we'll look at it here below. You can see a preview of it. Visually, we have our input variables, which are all of the features. And then we have our output, which are the classes. But between those, we have some hidden layers. And these layers give the network its strength, I guess. You can think of it like that way. So we have a few in-between steps that are going to allow us to more accurately do these predictions. And so here I have 8 nodes in the first hidden layer and 4 nodes in the second hidden layer. And the number of hidden layers and the number of nodes in the hidden layers is not something that is written in stone. You have to just play with it. You could even say do some kind of a loop and try out a number of different network models that each use a different number of layers and nodes, and then see which one gives you the best error rates. Just for demonstration purposes, I chose these values. There's not a strong rhyme or reason to it, but it seemed to work well and it seemed to perform relatively well. So as far as why I chose those, there's not a really strong reason based on some deep analysis or anything. And then we're not looking for a linear output. And you can read more about that in the documentation, but this linear output is set to true if you want that activation function applied to the output neurons, but we don't. So now we get to plot the network model. This is really just to look at it. It's not for analysis so much, but it's good to see how it works. And to do that, we can just use this plot command and then feed it the name of the model. And then for Quarto, it has this little quirk where it can't draw all of the models that are generated, and there are multiple generated as part of the way it's set up. So just including this rep equals best allows the best one to be printed here in this document. So this is what it looks like. If you recall, the features of the data set had these 3-letter names, and so they all appear as inputs. Then we have a bias value of 1 for all of these bias nodes across the top. And all of the weights between the nodes are here in black text. Now, it looks like an absolute mess. You can't read any of it. It's not really that useful to do so anyway. But what is important is that you see there's 1 node for each input. And then there's a node for, well, there's actually 1 more. Yeah, there's 7 inputs and 8 layers in that next one, plus the bias. And then there's 4 nodes in that second hidden layer, and then the 2 nodes on the output for the negative and positive. So at the bottom, there's a note here that says the error was around 16, so it's relatively low. But that's what the network looks like. And again, it's not super valuable for any kind of real analysis purpose, but it is good to see it. The next step is the confusion matrix. And the way that this is done is first we use our test data, which again, were reserved. So we use that and do a prediction using this predict command with our model and the test data. So that gives us our predictions. And then the next line here is looking at those predictions, and it tells us which column contains the largest value. So it looks at each row and determines which column contains the largest value. And I wrote a note here. This simplifies the predicted values into either column 1 or column 2 representing the classes. So I didn't draw it here, but essentially for an individual, given their characteristics, whatever they are, what is the class, right? Is it negative or positive? So given a set of input values for those characteristics, what's the right label? And it returns a numeric prediction under negative. So it might be like 0.1, and then it might return under the positive label a 0.9. So the second column is much higher than the first column. So this command right here tells you that the positive column was the preferred prediction. And then I basically put all of that into a tibble. And there's a few conversion steps here for factors and characters and stuff. But I essentially combine all that into a tibble. And then I wanted to replace those numbers, which are just basically zeros and ones, with the correct labels. So anywhere where there was a 1, I'd call that positive and the other negative or something like that. And then that can be attached back to the data. So that's essentially a little bit of conversion here. So I get negative and positive instead of numbers. And now the next step is to actually do the confusion matrix part. It can be done with table. We're essentially looking at a table of these values for the labels, but I'm using this caret library to do that. So this is all I'm using it for. And what I like about it is that it gives you the table that we're looking for, but it also gives you more information on top of that. So it can save you time in terms of calculating things like the, let's just scroll down here. So sensitivity, specificity, positive and negative prediction value, stuff like that. So that's already done for me. And I'm specifically looking here at the accuracy, which is the number of true positives and true negatives divided by the total. So that's just an easy way to see if our network is performing relatively well. And I do want to revisit this idea that it's an imbalanced network. It's not, the data set was imbalanced. There's a lot more negatives than positives. So as far as what the network is able to learn about, it's more able to learn about the negative values than it is about the positive values. So the results here, the prediction is on the left side. This is the confusion matrix right here. So the prediction is on the left side and the reference is across the top. And so when there was a negative value and it was predicted as such, then, there was quite a few of those, 420 something. And then over here, we see roughly the same numbers for if it was positive and it predicted negative, which is not good, or if it was negative and it predicted positive, which is not good. And those both outnumber if it was positive and it was predicted positive, which is what you want. So ideally, perfectly, you would have all the information in the top left and bottom right, but that's not the case. And so what we see here is that generally it did pretty well with the predictions with almost a 96% accuracy. But if we scroll down here and look at the positive prediction value, which is great, 90.98 almost, we can see that the negative prediction value is pretty bad at 0.4. Now, one caveat here, one thing to mention is that the negative label, for which there were so many, is actually the thing that we're trying to detect here, which makes it the positive class, which is a little confusing. So that's why you see the positive prediction value looking for the negative label, right? So it's kind of opposite, sorry. But The good news is that it does do good detection on that, but not so much on the positive label, which is the negative prediction value. So as far as the overall quality of the network, it seems okay. It's not amazing, but a part of that is just that the incoming data were not balanced and maybe not as useful for what we're trying to do here. As far as how to set up a neural network and run it, I think this is a good basic example using the libraries that are available to you with R, and there's many more out there, but I thought this was a good example of how to do classification prediction in this system. So if you enjoyed this video, go ahead and like it, consider subscribing to the channel for more information, and stay tuned as I continue to work on this machine learning book that I started. Thanks. Have a great week. Take care.